Good morning, children. At least it's morning for me. As you can see, the background's a little different today. The wife and I decided we need to get out of the house. So we're at a beach. I think you can see the ocean behind me. Staying in our room, social distancing, only going out to the beach and back. But hey, it's better than going out to the backyard and back. Let me shrink down the camera and let us begin today's lesson, which is going to be on electricity and magnetism, how the two are related to each other. So, hopefully you have your notes printed out, or if not printed out, at least you have a piece of paper you can write down your notes. Here we go. Electric current creates a magnetic field around the wire through which it is flowing. So that should answer the first question on your notes. All right. If there's more current, the stronger the magnetic field. Also, the field is stronger the closer you get to the wire. Let me move my picture out of the way. There we go. Field is stronger the closer you get to the wire. So two ways to make it stronger is more current or just get closer to the wire. Pause if you need to. I am moving on. Okay. Now that you know that, you can understand how I make this thing called an electromagnet. So the definition of an electromagnet is you make it by wrapping a wire carrying a current around a piece of iron. I'm trying to put the picture somewhere where it is not covering any words. That's close enough. Wrapping a wire carrying a current around a piece of iron. So you write that down and I'll explain how it works. Pause if you need to, because I'm moving on. See, what happens is the magnetic field around the wire overlaps itself when the wire is coiled around something, increasing its strength, so it multiplies itself. The magnetic field forces all the domains in the piece of iron to also line up, creating an even larger, stronger magnetic field. So what we have here is electricity going through a wire, which I can control. I can control the amount of current. I can control if it's on or off, creating a magnet. I can turn it off, the magnet turns off. I turn it on, the magnet turns on. A magnet you can turn on and off and control the strength of. It's a pretty cool invention, and it's used in many, many things in your life. All right, the coiled up wire is called a solenoid. So that's the definition of a solenoid, a coiled up wire. Not a very complicated definition, is it? And yes, my coffee cup is smaller. I didn't bring one with me. All right, properties of electromagnets, or how electromagnets beat normal magnets. They're temporary, which means they can be turned on and off in this case. I can control the strength by either changing the amount of currents or the number of coils. So I can turn it on and off, and I can control the strength. The two ways electromagnets beat regular magnets. Alrighty then. Again, remember you can pause anytime you need to if I'm going too fast. What are electromagnets used in? There's three things. Speakers. All of you have speakers. How is she listening to me right now if it's not a speaker of some kind or other? Galvanometers. Just write it down. I'll explain what it is in a little bit. And electric motors. Anything in your house that spins has an electric motor. Alrighty then. I think the first one is the galvanometer. So here's a cartoonish picture of a galvanometer. Does this look familiar? Like, look at just from here on up. Looks like something in your car's dashboard, doesn't it? So down here, the part you usually don't see in the dashboard, you have this round gray piece here is a chunk of iron. The red is a solenoid, wire wrapped around it. The black spiral is a restoring spring, they're called. Kind of spring where if you squeeze down on it, it wants to pop back out. And then you see the big N and the big S. That's the North Pole and the South Pole of a permanent magnet. So you have this permanent magnetic field around this solenoid. Put electricity through the solenoid. It has a magnetic field. Two magnetic fields interact with the force. Forces cause accelerations, so the needle accelerates to the right. The more current going through the wire, the more this needle gets deflected to the right, like in your gas gauge in your car. Most gas tanks have this floaty bobby thingy inside of it. The higher it floats, the more current goes through this particular solenoid right here, and the more this thing deflects over towards the full label. So that's how a galvanometer works. When you turn off the power to it, the restoring spring forces it back to the left. Okay. Speaker. So you have a permanent magnet here, solenoid here, and you have electricity going through the wire. And it reverses direction rather rapidly. Every time it reverses direction, this here voice coil, which is an electromagnet, gets either pushed up or pulled down. That's what causes the vibrations, which make the sound waves coming off of this, the actual diaphragm. If you ever blow a speaker, you've either broke the suspension or you broke the spider down here. This, now if you were in my classroom, I'd have had this at the beginning of class. I built one myself and I have it spinning for you. It's pretty cool. This is a poor man's electric motor. You have a D-cell battery, a permanent magnet, a one wrap solenoid, so I don't know how fast that would spin, but whatever. And paper clips just to connect electricity. This wire connects electricity, so what you have here is a magnetic field around this wire interacting with this magnet's magnetic field, causing it to spin. It's trying to basically repel it, but it can't go anywhere, so it spins in place. That was my phone being loud. Alright, that's basically how electric motors work. You have a permanent magnet, you have an electromagnet, you put power to the electromagnet, and because it can't go anywhere, but it wants to be repelled anyways, it'll spin. That's how you get things to spin. I have oversimplified the heck out of it, but that's okay, it's just high school. We also use electromagnets to pick stuff up, like this. I'll go back to electric motor for a minute. What in your house spins? You have some microwaves have a spinning plate in them. You have CD players. You have some of you have record players. They're making a comeback. Don't know why. You have DVD players. You have Blu-ray. You have gaming systems. You got to put a disc in it. Fans. The fans in your computer that cool it down. Anything that spins, electric motor. Alright, pick stuff up. This kind of thing you see at a junkyard only picks up steel. Remember, only iron, nickel, and cobalt are affected by magnetic fields, so aluminum cans wouldn't be touched by this. Wouldn't be picked up. And thankfully, this doesn't happen. Unfortunately, you can't see the bottom. There we go. Oh, but that looked weird on your screen there. Little cartoon. You can pause on it and look at it if you want to. I'll put this back up where it was. And move forward. Producing electric current. Alright, so we're on the other page of the notes. If you move a loop of wire within a magnetic field, an electric current is produced in the wire. See, what happens is the electrons that are loose try to follow the positive pole of the magnet. So you move the wire, the electrons try to move within the wire to stay close to that positive pole. And also repelled by the negative pole. You keep moving that wire over and over again, the electrons are moving through the wire. They're trying to stay put. Because the wire is moving, they got to move through the wire. That sets up a voltage difference through the wire, a pressure on the electrons, and they start moving. That's an electric current. You can also move the magnet if you want to. So it doesn't really matter which one you move. You have to have some kind of relative motion. You can either move the magnet or the coil of wire. Doesn't matter. Either way, mechanical energy is changed into electrical energy. More energy transformations. We're still on that. That is the opposite of an electric motor, where electrical energy is converted to mechanical energy. In my class, you might have hand crank generators. If you attach them to each other, you crank one, the other one starts spinning. You're converting mechanical energy into electrical energy through the wire back into mechanical energy. It's pretty cool to watch and to play with. Unfortunately, not in the classroom. I'm at the ocean. Okay, I'm going to ignore this picture because we're not in the classroom right now. Alright, so for this to happen, the loop and the magnetic field must be moving relative to each other. So here's some fill in the blank stuff on your notes. The loop and the magnetic field must be moving relative to each other. Remember, you can always pause if I'm going too fast. It's a video. You have the power. This process is called electromagnetic induction. Generators use electromagnetic induction to transform mechanical energy into electrical energy. Yes, I can read. I have a generator in my house. Use it during hurricanes. I've had to use it, what, once now? Use it? Yeah, once. It was pretty cool. Kept my fridge and freezer going. Alrighty. So here in writing, I explained what I explained to you in talking. I'm just going to hit through the buttons. Y'all read it. There we go. Pause if you need to. I'm moving on. Okay, so because the current changes direction, this is called alternating currents. Abbreviated AC. That's not what batteries do. Batteries only have current flowing in one direction, from negative to positive terminal. We call that direct current, DC. This is how the group AC/DC got their name. What? It is. I looked it up. My wife's giving me eyes over there. I looked it up years ago. It was on the side of their mom's vacuum cleaner. It could either go AC or DC. It had a little lightning bolt in the middle, so they made that their symbol, AC/DC. Look it up. That'd be a good question for this, to see if they actually watched the video or not. Which rock group did I mention? Yes! Let's see some of you screw that up and just come up with a random one, like you've been doing. I'm bitter. Just a little bitter. Okay, your home uses alternating currents. The most common way to produce alternating current is to spin a coil in a magnetic field, or a magnet inside a coil. It doesn't really matter. The point is, you need a source of mechanical energy. The power company uses some kind of source of mechanical energy to get the generator spinning. The coil of magnets are attached to this thing called a turbine, which is basically a big wheel with lots and lots of little blades on it. Think about a fan with 1,000 blades. So it catches every little puff of air. What can be used to move this big wheel? Well, there's quite a few things. First off, wind. Let me get my face out of the way. So for scale, down here is a little door. That would fit this guy. Walk in there, I guess there's a ladder or a spiral staircase or something inside that you climb up, because these things need maintenance. This is not a windmill, it is a wind turbine. Windmills are used to crush grains into flour. That's what mills do. This is a turbine. It uses the spinning motion to make electricity. Yeah, some places really got their wind game going on. You see a huge, just, I don't know what you call this, a field, but it's over the water of wind turbines. And there's a little boat for scale. Alright, we also use water. Move that out of the way. To make the turbine spin. This is a cartoonish view through a cross section through a dam. Not the cuss word dam, the other one. So back here is a fake lake called a reservoir, which has been blocked up by the dam. Here's your intake for the generators. Turbine's down here underneath the generator. Penstock is a tube through which the water flows. You don't have to memorize all this stuff. I'm just showing you how it works, all right? This metal grating here is to keep fish, rocks, dead bodies from the mob out of there, so it doesn't get in there and gum up the works. And the pressure of this water, deeper the reservoir, the more pressure there is, causes the turbine to spin, spins the energy of the generator through the shaft right here, creates electricity, goes off to the world. And here's the rest of the river down here. The water goes back out to the river. So that's a cartoon. Remember, the generators are in the powerhouse. Here's a view of the Hoover Dam in Nevada, damming up the Colorado River, making Lake Mead. the reservoir back there. Again, for scale, these little dots down here, I don't know if you can see them on your device, those are cars. So are these. This is actually a road going across the dam. I'm not sure if you can drive it anymore, but back when I went there, back in the 90s, you could. Down here is the powerhouse. You see 1, 2, 3, 4 sets of towers sticking up out of it. That's where each generator is. The generators are huge. Each one is bigger than the size of my classroom. And you have 1, 2, 3, 4 gate controls up here. They don't have to run all 4 turbines at once. In the summertime, they may run 3.
I don't think you can go down there anymore.
No, you probably can't. But back in the 90s when I went there, I could. You did too? What year?
I don't know. I remember the joke the guy told us going down the elevator.
Can we say it here?
It was a damn joke.
No, never mind. I'll go ahead, say it. I'm not getting in trouble.
The guy said, because my friend was just being funny. He was trying to be funny. And then the elevator guy goes, "Son, leave the damn jokes to the damn professionals, and I'll let you damn know when the damn get here." Because damn.
Yeah.
Going the elevator down to the Hoover Dam. It's like an 8-minute.
It is.
Yeah.
It's a long elevator ride.
It's funny.
I think the visitor center is up here. This little thing there. Have you ever played Fallout New Vegas? Part of the culmination of the main quest line is at the Hoover Dam. And they got this part up here pretty well done on the, whatever it is. Okay. In the game. So anywho, that's how it works. So if they get 3 of these working at the same time, max maybe during the summertime, the 4th one is down for maintenance. You can always just switch from one to the other so you can keep them maintained. If they ever needed all 4 working at once, that's just way too much power needs. These are towers that take electricity lines everywhere else. You can barely see them because, they're thin. More cars up there for scale. Lake Mead nowadays is way lower than this. They're going through a drought right now, so yeah. That's not good. Okay, the main way, though, people have been spinning them turbines is with steam power. Here's a cartoonish image of a coal-burning power plant. Let me move this frame down a little bit. There we go. So you got pulverized coal coming in here with air, burning the coal to boil water. Water boils the steam. If you ever made tea in a teapot, you know when the water is ready because it starts whistling. The steam is under so much pressure, it comes out fast enough to whistle. It's done. Well, steam is under pressure, comes here, spins the turbine, which spins the generator, which makes electricity. Then the water is cooled and recycled through the system. Problem with this is this stuff up here, the stuff that comes out of the stack. Combustion gases, poisonous, nasty, causes this thing called acid rain. There are things you can put in here, filters that can capture some, if not, definitely not all, but some and a lot of those combustion gases. They're expensive. You have to replace the filters all the time. The company can recoup some of that money by selling those combustion gases that are captured to places like battery manufacturers because of the sulfur compounds they use to make sulfuric acid for batteries. But still, it costs a lot of money to do that. Alrighty. Steam, let me move this up, requires hot water. Water can be heated by using coal, as I just showed you, natural gas, same process, only less smoke coming out of it, or nuclear fission reactions. About a little less than half of the power companies in North Carolina or the power plants are nuclear power plants. A little less than the other half are coal or natural gas burning. I think we mostly converted to natural gas in North Carolina. So this is a coal burning plant. Can't get my face out of the way, sorry. See smoke coming out of it? Bad. Here's a nuclear power plant. Put my face down the river. So this is just steam coming off of it. Perfectly safe. These two are not working. These two melted down in the 70s. This is a picture of the 3 Mile Island nuclear power plants. I wonder why it's called 3 Mile Island. Oh yeah, look, it's on an island. For scale, there's a parking lot with cars, so these are big buildings. These two had a partial meltdown, so they just left it there. They took out everything they could, and they keep the other two running just fine. If you ever watched the movie Wolverine Origins, the ending scenes were based here, the island. But I digress. So it's a little more complicated, even in this cartoonish version. I'm just going to explain it. You ain't got to write this down. And here you have nuclear reactions that are heating up the water to really, really hot. Hot water comes through here and exchanges its heat with the water in the steam generator to turn it into steam. So the water in the reactor never leaves this reactor system here. Through the contact with the pipes, it heats up this water here. The steam spins the turbine. Oops. Spins the generator. The steam is cooled off by water from the river, recondensed back into liquid water, comes back here and is reheated again. So this water stays in a cycle, doesn't go anywhere. This water stays in the cycle, doesn't go anywhere. These two waters don't mix, hopefully. And this is just water from the environment, which goes back out into the environment. Okay, so there's this thing called control rods that are basically up in here. You lower them down and it absorbs the loose neutrons and controls the fission reaction, slows it down. You're not going to stop it because this uranium is naturally fissioning. But it can go faster because neutrons can hit other atoms and split them. If you absorb the loose neutrons, it's not happening anymore. They're just splitting at their normal rate, which is not very high. If the control rods don't go down in there, you won't get a nuclear explosion, but it'll get so hot that it could actually melt the fuel rods, the little pellets of uranium, and some other stuff in there. And so if they get hot enough to melt, it just goes down to the bottom of the reactor chamber, makes a slag. Down here, slag is molten metal at the bottom. If it gets hot enough, it can melt through the bottom into the ground. That didn't happen at 3 Mile Island, but it did happen in Chernobyl. So this is a helicopter picture after the disaster. This happened in the 80s, I think it was, Chernobyl. I believe it was the 80s.
What was?
Chernobyl.
86, I think.
Yeah, something like that. It was an HBO documentary. Watch it. It's awesome. Well, not a documentary. It's a docudrama, but whatever. Watch it. It's pretty cool. The Russians call it propaganda, but whatever. Either way, it went boom. It wasn't a nuclear reaction. It was a steam explosion. All right. The water in there got so superheated by the nuclear reaction the fission reaction going out of control and getting so hot that it all flashed of steam at once and poof, blew the roof out, taking a lot of that liquid core with it. The melted core material went out with it into the environment. So that whole area is hot. Huh? Oh, not me? Okay. If you ever played the game, yes, I know I'm using games. What was it? Call of Duty 4 was based in the town of Pripyat, which is where the workers for the Chernobyl plant lived. It was abandoned right afterwards. If you ever actually see pictures of Pripyat and you've played the game, you've seen the map of the game, yeah, pretty good. Again, they did a pretty good map job of the game of a real place. Okay, this is where Chernobyl region is. This is the country of Ukraine. Back then it was the Soviet Socialist Republic of Ukraine before the fall of the Iron Curtain. And nobody in Russia, in the USSR, told anybody that this had happened. They didn't tell the outside world. The outside world found out when somebody up here in Finland, Denmark, one of these Viking countries, went to work inside his own nuclear power plant that he worked at, and he tripped the radiation detectors on the way in. Normally those are for when you leave to see if you've been exposed to something at work. He walked in and tripped it. They did an investigation. It was on his shoe. He walked to a puddle. The puddle, it had been raining recently, was radioactively hot enough to trip the detectors. And so all they had to do is trace the weather patterns over the past few days and realize that rain cloud had come from this region here. The storm cells started here and gone up there. So the whole world said, USSR, what's going on? And they admitted, yeah, we had an accident. So there you go. Here's the hole that got blown out. It's pretty big. There was a building there. Okay, one you may remember, though it's long enough ago, I think y'all too young, is the Fukushima Daiichi Japanese nuclear disaster. Poor planning on this one. Oh, I'm sorry, I forgot to tell you. This one was also a poor design. Their control rods needed electricity to the motors to go down into the reactor and cool off the reaction. They lost power when they were up, and they couldn't put them back down. So they couldn't stop the reaction. They couldn't slow it down and cool things off. Control rods here in the United States and most other countries don't do that. They need power to be lifted up. If they lose power, boom, it slams back down. They literally, if the whole plant loses power, the control rods slam into place and start slowing down the reaction. Pretty good safety measure. In Japan, the problem was their backup generators were in the basement. Now, a couple years before the tsunami that caused this problem, based on an earthquake that happened, the Japanese people had realized, oh crap, that's bad design. Backup generators shouldn't be in the bottom because if there's in the basement, because if there's a tsunami, it'll flood them. So they started moving them up into a higher area. They hadn't got them all moved yet, though, when the earthquake hit and triggered the tsunami that flooded the basements. So they had some exploded nuclear reactors. The area is still hot and you can't go there. That's the PowerPoint. Thank you for sticking with me for 26 minutes. Y'all have a lovely day, and I'll see you next time.